Hi class. In this video, we're going to talk a little bit about the first two sections of chapter 5. And these are going to be the only chapters or the only sections of this chapter that we cover in this course. It's just a little bit of an introduction to what you do when you have systems of differential equations and some kind of notation that you can use to simplify and solve them. So we'll start off with an example here of uh, we saw some we saw mixing problems and like tanks before in chapter 3. And so this is a problem with two interconnected tanks. So here's the picture from the book. And what we have is we have two tanks that have brine in them. We have fresh water going in at 6 liters per minute here. The initial um, strength of the brine, like the salt solution inside, is given um, with these initial conditions. So initially you have, X naught or Y naught kilograms in each of salt in each tank. The solution is leaving the second tank at a particular rate. And then we also have these mixing conditions that are given here in the middle. So just like we did when we only had one tank, we're considering these quantities um, X and Y. X is going to be the mass of salt in tank A, and Y is the mass of salt in tank B. So we'll just model each of these kind of by themselves, just in the same way that we learned how to do before. And that was by using this idea that dx dt equals the input rate minus the output rate. So what's going into the tank? Well, going in is fresh water from that side. So that's just going to be, that's 0. There's no salt in that water. But you're also getting an input from over here. And so that is 2 liters per minute times the concentration of what's coming in there, which is coming from tank B. And so that's going to be Y kilograms per, and there's 24 liters of water in that tank. So the concentration in tank B is this quantity here. Let's do that in yellow. So that's the concentration in tank B. I'll make the observation that the volumes of the tank are always staying constant because you've always got 8 liters going in, right? 6 plus 2. And then you've got 8 liters going out. And same thing over in the right-hand tank. You've got 8 liters per minute going in and then 6 and 2 going out. But we would be able to deal with this even if it was non-constant. So anyway, that's the sort of second input. And then this should be a plus right there. So these are the inputs coming from, so that 0 is the input from this part right here. And this here is the input from that tank right there, or that tube, that pipe. And then the last pipe is an output rate, is the only term in the output rate. So we'll do a minus, and now we'll have 8 liters per minute times the concentration in tank A. So that's going to be X kilograms per 24 liters. Okay. So this is, let's see, I'll draw this right here goes with this pipe going out. Okay, so this is what we were modeling here is the, it's not necessarily restricted to tank A, but we're modeling the equation governing x here. So let's simplify this a little bit. So we've got dx dt equals 1/12 y minus 8 over 24, which is 1/3 x. Okay, so similarly, let's model what's going on with y. So dy dt, again, is going to be the input rate minus output rate. And what do we have going in? Well, first we have the quantity coming in from tank A. So that's going to be 8 liters per minute times x over 24 kilograms per liter minus what's going out. First, we can do the bottom middle pipe there first. So that's going to be 2 liters per minute times what's coming out of tank B. So that's y over 24 kilograms per liter. And then we have to subtract one more, and we'll do now the pipe going out at the very end. So that's going to be 6 liters per minute times y over 24 kilograms per liter. Okay, so to simplify, we get 1/3 x minus 1/12 y minus 1/4 y. And so we can simplify that down and we get dy dt equals 1/3 x minus 1/12 plus 1/4 is 1/3 y. So putting that all together, we get this system of equations governing the tank system. And so I'm just going to rewrite what we put down before, write it together. So now we have an x prime equals negative 1/3 x plus 12y, and a y prime, again, that depends on both x and y. So we have this interconnected system or coupled system. And that seems like it would be pretty complicated, but actually, if we look at this, it's pretty easy to see what's going on. But before we go too far, let me fix this little error that I made. So this is 1/12 y there. That looks better. Okay, so now let's go to blue, and we can see that in the second equation, we can multiply that through by 3, and we can actually solve for x. So we get that x equals 3y prime plus y. And then we can substitute that into the first equation. And that will get rid of the x's. So we get x prime is going to be 3y prime plus y, that whole quantity prime, right? Minus 1, or equals negative 1/3 3y prime plus y, and then plus 1/12 y. And let's just work this through. So you get 3y double prime plus y prime equals negative y prime minus 1/3 y plus 1/12 y, and combine everything together on one side, we get this equation, 3y double prime plus 2y, and then 1/3, -1/3 plus 1/12 is -1/4, flip it to the other side, plus 1/4 y equals 0. So this is neat because this here is we had two first order equations up here, but this is a second order linear equation with constant coefficients. And so we know how to solve it. And so the solution here is, I'm just going to write it, y of t equals c1 e to the negative t over 2 plus c2 e to the negative t over 6. And you can verify this. So now that we've got y, shrink that down a little bit, and we can go back to blue. We have an expression for x in terms of y. So now we can say that x of t equals 3. Now let's take the derivative of our y here. So we get negative c1 over 2 e to the negative t over 2 minus c2 over 6 e to the negative t over 6 plus y. So we get that same expression again. c1 e to the negative t over 2 plus c2 e to the negative t over 6. And we can simplify this down and we get this quantity, negative 1/2 c1 e to the negative t over 2 plus 1/2 c2 e to the negative t over 6. So now we have expressions for both y and x. And we have initial conditions. So we can solve for those constants. So x of 0, if we plug in 0 here, we get negative 1/2 c1 plus 1/2 c2 equals x naught. And y of 0 equals c1 plus c2 equals y naught. These can be solved together, and that gives us these quantities. C1 equals this, and C2 equals this. And you can verify all of this if you like. And then we can get final answer. Switch back to blue. Looks like this. So you might think, well, maybe this was just kind of simple and we got lucky that we were able to do this kind of algebraic manipulation. But the observation here is that we can treat differential equations a little bit like algebraic equations. So to make that a little bit more explicit, we're going to use some new notation. So I'm going to use some notation referred to as differential operators. So an operator is like a function that takes another function as an input. And a differential operator is an operator that has a derivative in it, right? So you think about the notation y prime of t that's sort of our shorthand for the more formal dy dt, which you can also think about as d dt of y. And we use it like this a lot. And so we're going to now define the symbol d. So those dots mean that I'm defining this here. Capital D is the differential operator that I'm referring to. It's just the operator which takes a derivative. And to show that I'm operating on of the function, I use brackets. So let's be a little explicit here. So this is the derivative, and then the brackets mean that it's operating on y. So now with operators, when you put them next to each other, when you kind of treat them like multiplication, that is interpreted like composition. So if you have something like d of y, so that's the derivative of y, we can write this like d squared of y. So then we can write things like y double prime plus 4y prime plus 3y equals 0. Well, we can think about this like d squared of y plus 4 times d of y plus 3y equals 0. Make the observation that 3y is like the same as saying 3 times the identity operator, which just leaves a function alone. And we could also write this like d squared plus 4d plus 3 operating on y equals 0. So what's nice about this notation is that the part in parentheses here looks like a polynomial. And polynomials we can do a lot of fancy things with. And we see in some cases you can treat this like a polynomial and it makes sense to do so. So let's make an observation here. So if this were a polynomial, we could factor it into d plus 1 and d plus times d plus 3. So the question is, like, can we make sense of this factorization? Well, let's think of what d plus 1 times d plus 3 operating on y would be. So remember, multiplication is like a composition. So first you would do, let's leave this d plus 1 alone. You would do d plus 3 operating on y. And so that would be, oh, sorry, that should be like square brackets there, right? So we'll leave this d plus 1 alone, and it's going to operate on this step in here. So that's going to be d plus 3 operating on y is y prime plus 3y. And now if we do the derivative plus of this thing plus itself, that's going to be y double prime plus 3y prime plus y prime plus 3y. And then if we simplify this together, we get y double prime plus 4y prime plus 3y. And that's the same thing as what we had up here. So that's d squared plus 4d plus 3 operating on y. So that's super great. That shows that we can factor this sort of differential operator. However, this only works if you have constant coefficients. So the result here is that we can factor differential operators like this if they have constant coefficients. So an example that I will leave to you as a reader, or you can read it in the book, is when you don't have constant coefficients, it doesn't necessarily work out. So d plus 3t times d is not equal to d times d plus 3t. And so you can't even commute them. Now you could commute in the constant coefficient case, because if you like, we could do the same thing if we flipped d plus 3 and d1, and it will equal this, and then d plus 1 times d plus 3 would equal d plus 3 plus times d plus 1. So as a matter of fact, I mean, I could really elaborate on this here. You can factor and do all other types of polynomial algebra on differential operators whenever you have these constant coefficients. So to be a little bit more explicit about this, I'm going to let L1, L2, L3, and L4 be linear differential operators. Which is to say polynomials in D. Then we can use this elimination method on a linear system with two equations and two unknowns. So just like we had in the last example, we had an unknown x, and an unknown y, and we ended up with two equations for them. And so that system will have some stuff with x's in it, including derivatives, right? L1 x plus L2 y equals something, f1. And L3, our second equation looks like L3x plus L4y equals F2. So remember, these L's have derivatives, maybe multiple derivatives in them. It's like a polynomial of derivatives. And so these are just like the equations that we saw way up here, where if we sort of shift everything to one side, we had some derivatives of x and derivatives of y, and x and y themselves all mixed together in the equations. And because these have constant coefficients, we can add and subtract and multiply and commute things and factor things and all that. So we just sort of eliminate things the same way that we would do in a regular algebraic equation. So let's say we want to eliminate y by doing L4 to the first equation and then subtracting L2 of the second equation. So that gives you L1, L4 minus L2, L3. We now, like the y terms cancel, so we just have an x, and then what you're left with on the right-hand side is this. And similarly, we can eliminate x, and it gives us this quantity here. So just like we saw in our examples, we're left with an equation in just x and just y, and we can solve because these are linear equations with constant coefficients. So even if they have higher order than 2, we learned in the last chapter all the theory for being able to solve these with constant coefficients. Now, when we solve, the weird thing is that we'll be left with sort of twice as many constants as we want. So if L1, L4 minus L2, L3 is a differential operator, which it is, but if it has order n, that is an n that I underlined, then we'll end up with 2n constants because you'll get n from this equation and n and another n from this one. But one set can be written in terms of the other. So this is sort of hard to explain. I mean, I guess the point of this is that there is a system of solving these. Now, sometimes this might end up being 0, and you get left with this kind of degenerate equation. Just like when you have a linear system of algebraic equations, you might not be able to come up with a solution. So this isn't a proof of existence or anything like that. It's just a demonstration of a method that can be applied very generally. And so I'm going to leave, this video is getting really long, and I've done the like really weird abstract stuff. And so I will leave you to read through the example in the book really carefully. And those will sort of give you some understanding of how you would do the homework problems. And then I'll make one last observation here is that what we've done here is we've turned solving a really complicated system of um, of equations into a simpler sort of algebraic problem, something that we like learned how to do in high school. And I'm not going to go through, I think one of the examples has a system of 3 equations, but that starts getting really cumbersome. And so in theory, you might have a lot of systems working together, right? Because every quantity, so let's go back to the beginning. So every equation, you have like one equation for each quantity that you're trying to solve. And so in this example here with the tanks, you had one unknown quantity for each sort of physical component. So you can imagine a physical system where you have a lot of different parts working together and you'll have one equation for each piece of it. And so you know that if you were trying to solve a linear system of equations, like just like in algebra, and there were 10 equations and 10 unknowns doing this like um, substitution method and elimination and everything would get really awful. So that's where linear algebra comes in. And that's where you started learning how to write things in terms of matrices, right? And then you could solve the matrix and you wouldn't have to do elimination and everything like that. And so we're not going to cover this in the class, but linear algebra can help us approach more complicated systems of equations. And that's why it's important to learn linear algebra, even if you, I don't know, think that you're going to be a differential equation solver in your adult life. So anyway, that's the observation here. This is the only section in chapter 5 that we're going to cover. So I just want to give you some practice using this kind of notation to solve these systems. And so that's what the homework will be about. And then in the rest of the class, we'll go on to chapter 7, which is the really hard, really fun stuff of the course.